All right. So today I am going to talk about this idea of robots with a twist. Metamaterials enable direct drive compliant robots. Feel free to stop at any time and shout out with questions. I do it all the time. Um, all this work is really made possible because of my collaborators, but most importantly, the students who come through my lab at the Transformative Robotics Lab as we've moved from University of Washington to Northeastern. So as I mentioned, a little bit of background about myself. I started my engineering career on the Fab at Home project. We made 3D printers. They could extrude goo. We used it to make cookies and that you could slice the middle and have chocolate writing on the inside. We used it to make even body parts like this human ear and heart valves. And we supported researchers on all 6 habitable continents. And then I had the great privilege of starting my professorship right as COVID happened. And so I turned my entire lab into a 3D printing PPE studio where we worked on the first FDA approved face shields and face masks where we supported the validation of them. We developed some of the first face masks that were emergency use authorized. And we worked on a wide range of projects related to COVID and 3D printing. And one of our partners in this was Ford. And Ford, their response was phenomenal. They set up a manufacturing line to produce face shields, and they got all their human workers together in a room and said, just go start making face shields. And this begs a really important question. What is wrong with robotics that in the middle of a pandemic, we decided the most efficient way to spin up manufacturing was to throw a bunch of humans in a room? Right? And not only this is Ford. They're one of the early adopters in automation for manufacturing. And their solution was just throw people in a room when you want them as isolated as possible. And so this begs this really deep question. How can we go from manufacturing cars to manufacturing COVID supplies? How can we add this flexibility and how can we improve robotics to solve these problems in the manufacturing chain? And so my fundamental thesis is that the problem is partially with the robot bodies. And what we really need to do is to use robots to create novel materials and manufacturing methods, and then use those novel materials and manufacturing methods to enhance the capabilities of robots. Because I'm sure you're all aware, really at the base of robotics, right? One of the key layers is that materials drive robot design, right? If I've got steel components and plastic hard, I can give direct drive. If I start to add a little bit of compliance, you can get series elasticity. And then you have this other world of soft robotics where you have origami and new-nets and dielectric actuators and hazels and all these other exotic things that are very different materials. And the question I want to know is, can we bridge these two worlds? Can we have a world where we still hold on to the legacy of motors and get all the benefits that soft robotics promises? And to do that, we have to look at the basis of robotics itself, right? We're all familiar with this diagram, essentially, right? All robots break down to, in rigid robotics, revolute and prismatic joints, right? You just have your DH parameters, they go around, they transform, and then you've got some gripper at the end that does your interaction with the environment. And so what we want to see is, can we take this structure and break down our understanding of prismatic joints, revolute joints, and grippers, and rethink them from a materials perspective so we can fuse motors in with the robot bodies to get the benefits of soft and hard robots so we can solve meaningful manufacturing tasks. So let's start at the beginning, right? We want to rethink the prismatic joint. Well, people have been looking at prismatic joints from a materials context for a long time. The original one is twist expansion coupling from the Kresling pattern. It's an origami fold pattern that when you twist, you get extension. And a lot of work has been done in this space to understand and build these. But what I said is, well, what we really want is a structure that's a cylinder that can twist and expand. And if we want it to twist and expand and live on the surface and have strength and properties, it's going to have a couple properties of its own, right? This structural transformation inherently says you can't use rigid elements, right? I have a beam and it goes around on a circle. Its curvature is changing. It can't be rigid. All right, we need compliance. The other thing it means is if we take this type of structure and look at it from, take the cylinder, split it in half, fold it onto a plane, we have a rectangle turning into a parallelogram. Well, that parallelogram also gets bigger. So we call that getting bigger being auxetic, and the transformation from a rectangle to a parallelogram is shear. So what we really need, if we're going to rethink these prismatic joints, is a compliant auxetic shearing material. And on credit, give it to me that we want it to be handed. And what we discovered is that there are actually many ways to build these handed shearing auxetic patterns. You can do it at the pattern level, the joint level, and the alignment level. But let's first really dig into that idea of what does it mean for something to be auxetic, for something to get bigger. Well, if you look at it, this is an old pattern, rotating squares. They have a single degree of freedom theta. And if you imagine a lattice over these rotating squares, you can then define two lattice vectors, L1 and L2, and they must be in a triangular arrangement, right? They're going to point in this way. They're a triangular matrix. Well, they're going to change in some way. They're going to expand as this L1 and L2 goes, and it's going to be driven by the internal angle theta. And so we can look at the properties of that and say, well, as theta increases, the structure expands, reaches some maximum, and comes back down, right? Those are auxetics. And we can then say, well, what symmetries exist? Where can we find these auxetic patterns? And it turns out, if you look at the world, you find all kinds of different auxetic patterns in literature. And we need a way to describe these different patterns if we're going to make sense of how to transform these into these shearing auxetic ones. And it turns out the mathematicians give us a wonderful tool called orbifold notation. Orbifold notation classifies symmetries by either rotations with blue and the number 2, or star for a mirror. So you can get star, 2 mirrors intersect for star 2, 3 for star 3. And then you have these 2 other patterns where miracle happens, where you have a left and a right-handed approach each other without having to cross a plane. And then you have ones where they just tile off. It's called a wander. And from this patterns, we can take, or this nomenclature, we can define all the patterns that cover a plane. These are known as the wallpaper groups. And it turns out there are 17 of them. They're all patterns you'll see on any wallpaper or anything that tiles the plane repeatedly is going to fall into one of these wallpaper groups. And every one of them you can find an auxetic in. So here we have a 3 star 3 pattern. But if we go back to all these traditional auxetics, we can classify them and they have all these nice symmetries, right? So we've got 2 star, 3 star 3, 4 star 2, 4 4 2. They all exist. So say, okay, now we have the tool for understanding auxetics. Well, how can we combine it with shear? And what we can say is if we take shear, we have to combine it with rotation and reflection, and it has to form a closed group structure. And it turns out that only happens for a couple symmetries, right? Either no rotation, 180-degree rotation, no rotation but a mirror, or 180 degree with a mirror. And so we can find all of these, and it turns out we can roll out a lot of the wallpaper groups saying you'll never find a shearing auxetic pattern. But not only that, we can take these patterns and classify them in 2 ways. Some of them will have a shear and a mirror, and that doesn't quite make sense normally. But if you have the mirror at one point, the structure will shear up, develop a mirror, and then shear down. And those have no handedness. They can transition back and forth. And other ones are handed. They have a shear, no mirror, but if you make a mirror, you get another handed pair. And so we can classify all these structures into either handed or unhanded shearing auxetics based on the symmetries they produce. But not only that, we have a tool for taking any auxetic pattern and making a shearing counterpart. We just take it to its maximum, expands, apply a shear transformation to it, and now you have the shearing auxetic counterpart. There's a lot more math you can look at underneath the structure for the group theory of the properties of what we're going through. But basically, by looking at the transformations, you can classify any auxetic pattern into either a standard auxetic, an anisotropic auxetic, or a shearing auxetic by just looking at this group theory math. It's a lot of math to build something that when I put a weight on it, it pulls to the side, right? Not that impressive. But if I take it and I pattern these on cylinders and change their clocking and handedness, I can now apply them and I can get structures that counter-rotate to expand. And this allows us to then make actuators. So here is the original work where we apply a twist at the base, it extends, and then it contracts. We can get pretty long extensions out of them. If you take these handed shearing auxetics, put them into a 2x2 array, you can get a Ford-off platform for a section of a robot wrist where it can extend, bend in each direction, and twist. And if you add constraints to these structures, you can actually get them to bend. So this is work I did with Lily Chin, who's now at UT Austin, where we can apply twists at the base. You put it onto a robot, and you can make a soft robotic gripper. Very efficient, entirely electric, entirely motor driven, puncture resistant, much faster than a lot of pneumatic structures. There's just one downside. You need two of these things to make them go, and they're not as good against lateral loading, right? If you've ever built a soft robot and you try to grab something, you always see it kind of floops out of your hand. And so with my students Ian Good and Srivatsan, we built this structure where we use HSAs, but we can actually lift a 5 kilogram weight. And the only reason we were limited at 5 kilograms is it was the maximum payload capacity of the UR5 robot, and we didn't want to break it. And what it really comes down to is solving these problems in gripping, where normally you have a twist failure mode, right? You try to grab something, it twists out of the way, or you get out of plane slippage. And if you look at the failure modes in these types of grasps, usually you have a static component, a gravitational component, and a shear component that you're worried about. So it's either slipping, twisting, or shearing. And it turns out for soft robots, oops, someone has enabled translations. You need to solve this problem. How does nature solve this problem? Nature solves this problem by adding skeletons, right? This is what your joints do. And so what we found is we can actually add an entirely continuous compliant structure in a torsion-resistant strain limiting layer, and we can decrease this twisting mode. And what that allows us to do is make structures that are much, much stronger for grasping. So if we watch it again, right, this twist-resistant layer combined with a twist-activated structure allows us to use motors to transmit at the base to give you bending, only one of them, and get grasp objects and grasp with a lot more success. Okay, so HSAs, you can squeeze with them, you can lift with them, you can make a wrist out of them, but they've also been somewhat limited in their abilities before. And so what we've been looking at is converting from what we had before, which is just a one-directional actuator, a push actuator, into a push-pull or pull-only actuator. And by changing the internal properties of the HSAs when we print it, we can actually view this as a programmable spring element who can either be contraction-driven, expansion-driven, or both. And we can design how much holding torque we get. And so the most interesting thing is we can get higher blocked forces and controllable spring constants. And we've designed these in such a way that we can now give you a programmatic design, and they're even simulated now in Elastica, thanks to Cosimo, where he's been able to take our data and build an Elastica model for all of these elements. So we can model HSAs on a platform, we can build grippers out of them, we can build strength out of them. They're just a really powerful design tool in robotics to convert twist into push, pull, or pull-only actuation. What else can they do? Well, it turns out they're also deployable structures. If you take one of them, they're pretty weak, they collapse down. But if you pattern them, not in terms of left-right, they'll resist a little bit stronger, but all 3 layers alternating, left, or right, left, right, you get an interlayer jamming effect, and you can deploy and make a structure that's much stronger than if you just had one of them. And now with Zach Manchester at CMU, we've been working on a NASA project to make kilometer-scale spacecraft from a single launch. So we've been making deployable structures out of these. So not only can we build robot components out of these, we can build spacecraft out of them. But there's still more we can do, right? We mentioned these HSAs. We've got this ability not just to make deployables, but to change their minimum energy length, look at their holding torque. But the best question I've ever been asked about the HSAs came from Shuguang Li. He's now at Tsinghua, and he said, what makes this different from just a spring, right? Because springs, you could press them, you could apply a little twist, and what it turns out is they're not just springs, these are actually, so I can skip through these slides. Ooh. Whoa, too far. These are spring brakes. We can use these as programmable spring elements by changing their twist. and also use them in different ways and integrate them into robot legs to add capabilities that we don't normally have. So normally, if you think of a legged robot, right, it's got to walk around. So it can do, let's in 1D, that's just hopping, right? You can make a 1D hopper. And then it's also got to stand still and not burn energy. And it turns out standing still and not burning energy is really hard for a lot of these robotic systems. And what we found is, you can use this HSA and you can twist it in such a way that you have these different regimes of operation. In one regime, it acts as a programmable spring element in line, either parallel or series with the motor itself. But in another region, you can jam it out. And so you can twist it and jam it. So use that ability we found in deployable structures and apply it in a robot to make something so it's both a spring and a brake all in one. And what we found is when you put it in stable hopping, you can reduce the energy consumption, right? So just as you would expect from, say, a parallelistic actuator, you can add a spring in there and it saves a bunch of energy in terms of the motor work. And this is work we're doing with Sam Burden at University of Washington. But what we also have is this regime where you can twist it and now it holds. And so it is both a spring and a brake mechanism all in line. And so what we found is when you're using it as a jumping leg, you're using much less energy than if you didn't have the spring element there. And if you put it as a brake, you use much less energy to hold itself in place. So using an HSA as an element, as just a standard spring replacement in the system, you can hop for longer and stand for much, much longer. So we've been looking at all these energy landscapes and applications and design spaces. If you try to understand the whole spaces of where HSAs have been, we started off with my original work. Ian Good developed the push-pull version. Ryan Truby looked at different material properties. People have then found ways to make them applications in mobile robot systems, grippers. They've added self-sensing or tried to understand different ways of controlling them. But these structures have applications in robotics and stents and civil infrastructure and space applications. But it's all from asking this question, how can we make a motor-driven structure that acts as a prismatic element in a robot? Okay, so we've got our prismatic element that turns twist into expansion directly in the structure of the robot. The next question we want to ask is, what about rotation? Well, we talked about symmetries before. Our favorite symmetries were the wallpaper groups, right? Not just because they decorate offices, but because they're a nice symmetry pattern for understanding tilings of a plane. Turns out there's another set of tilings. These are the ones on spheres. And if you look at the tilings on spheres, there's some interesting things you can do. So with Lily Chin, we looked at this idea of, well, could we make twist-driven volumetric actuation? So we could make little cells that expand and contract. Turns out you can. This is also work done with Jacob Miskey when he was an undergrad at MIT. And we can take these structures and they can expand and contract. And then you can combine them together to do things like crawl under a thing, or actually even create locomotion by twisting the structure back and forth. So if these twist-driven cellular actuations, we can build things that look like this. So this is a paper that's coming out in ICRA this year. We can actually just cyclically control expansion to make a soft robot that can crawl across the surface. You can get turning. I'm going to skip ahead. See if we can get my favorite one. Here's the coolest one where you can get it to flip, where you can expand them, contract them. If you do it enough times, eventually you'll get yourself to flip over. There we go. Right? So you can have twist-driven actuation into this structure. That's all going to be driven by these cells over here that have, finite numbers of structures. These are well-known auxetic patterns. They've been in the literature for decades. But what we discovered is actually there's a whole other family, these ones with the n in there, where n can be any integer. And these have not been discussed in literature before. This is work with my student Molly Carton, who's now a professor at University of Maryland. And what we found is these are a new type of auxetic. And what they are is they're called axial auxetics. These are axial point groups. And what they define is an axis of symmetry around a sphere with an equator. That's exactly what we want in a rotational joint. And if you look at all the simple mechanisms you can put on these symmetries, you find that you get different mechanical properties out of them. Some of them are pretty straightforward, where you can take this point group, you look at the Freeze group equivalent, you can see how the structure transforms, and you can just get a sphere that twists the poles relative to each other. So again, it's a shearing auxetic, it just happens to be on a sphere. If you have the vertical freezes, it just expands and contracts, or it just gets bigger and smaller. But if you put a freeze with a horizontal mirror, you get something with an equator that twists relative to the poles. And this gives us a really interesting property where you can make structures that twist and can switch between an auxetic and non-auxetic region. And so if we look at this real quick, zoom ahead, right here is it cycling in the auxetic region, you apply a twist, I'm sorry, that's the auxetic region. Twist, it expands, or you pull on it, it expands. And here when you press, it gets wider. So it's non-auxetic, and you can switch between them. But what's really cool is you can tile these and either allow the equators to all twist, counter-rotating to each other, or the poles to all twist, counter-rotating to each other, or frustrate them. And if you do that, you get different switchable mechanical properties out of the structures. So if you have this polar rotation, right, in one version, you get this red line where it has a plateau on stiffness. The other one, you get a standard increase in stiffness. So we get programmable switchable stiffness from these structures. Cool, but not what we're looking for. What we're really looking for are freeze groups with an equatorial structure, right? If you find these patterns, the 2 star N or the NX, you can get a pattern that goes across the equator. And what that does is it locks the poles together so that the poles can't twist relative to each other on a sphere. And they look something like this. Okay, we've got poles, they're locked together, but you can pull on them, they expand, who cares? Well, it turns out they can flex. So they can flex and bend, but they're rigid against torsion. What does that mean? Well, it actually means you've made a CV joint, a constant velocity joint. But not only have you made a CV joint, it's a nestable CV joint that you can expand and contract while transmitting torque. So now we have an entirely compliant and nestable and expandable CV joint that's never existed before by looking at these auxetic properties. And it turns out if you take them, you can tile them together, and you can build this structure here where you've got a line group and it moves and bends. I should note, no one here is a reporter in the audience, right? No one's in the press?
Yes.
Okay. Just so you know, this information is under embargo for the next 4 hours because this is coming out in our science robotics paper at 2 o'clock Eastern time. And what we do is we can take this structure and we can build a line group. And what that does is it allows us to make a nestable chain of CV joints that we can bend and extend and transmit torque. Great. So we've got this line that can transmit torque. This is essentially, if you've ever played with a flex shaft, it does what a flex shaft does. It can also get pulled on. Okay, we can do that, but we wanted something that's even more torque than that. And we found these other structures where we can take them and they've got this equatorial band around them that's essentially a lattice. And that gives us the ability to put in enough torque to drive a screw into wood. Now we've all seen tools that can drive a screw into wood where you can change the angle, but now we can change the angle and lift up and down. Okay. Well, it turns out if you've got these structures, they're very stiff to torsion, but they can bend and flex. You can take them, you have these different torsional displacement properties, this ability to work under all these different conditions of shear, extension, bend. You chain them together, you get a flexible, extendable CV joint. You can nest them together, you can send multiple torques down the exact same pathway, and then you can combine them to make an entire chain of multiple torques being put down the same pathway and bending and extending. This is a key enabler in soft robotics. And the reason is right now, a lot of soft robots can pull. And one of the key ideas in soft robotics, they have to be able to push, pull, and bend, right? That's what makes a soft robot arm great, is it can bend and extend. Well, we take this and we can now make a robot arm that can bend and extend, and it can move with quite a bit of accuracy, but it can also transmit torque and do torque in the environment. So it can bend, extend, and transmit torque. What can you do with something that can bend, extend, and transmit torque? You can start to do real work, right? So here we've got an example of one robot screwing in a light bulb. Another robot can do multi-turn on a valve. And here on the other side, we have a human worker. This is Kuba, my PhD student, who is inserting screws, but then the robot can come along and insert the screws behind him, or not insert the screws, sorry. Speed up, can screw in the screws behind him, and it's entirely safe for the human to be around. So we built this soft robot arm that can extend, bend, and transmit torque by understanding this new type of material structure that we got at by trying to design a new way to build a material revolute joint. Okay, so we looked at handed shear and auxetics to give us prismatics. By looking at revolute joints, we got these nice point group auxetics that can transmit torque through bend, extension, and shear, and we can chain them together to build soft robot arms. Now we just need to do more effects on the world, right? HSAs can make some grippers, but what else do we need? We need better grippers to really interact with the environment. And so for the gripper component, I'm going to talk about these three technologies: programmable lattices, 3D printable foams, and 3D printable grippers. So this is work I did with Sawyer as part of his PhD. He is now doing a postdoc. And what we looked at is, can we take one structure and reprogram it to give us different outputs? And we call these transition controlled metamaterials. So we can take the structure, go back to the video. And when you compress it, here's the beaker. Take the same structure and reprogram it. Compress it and get a face. And we can, very accurately model these. And it's all built on this idea that we can take a single reconfigurable cell and transition it from positive to 0 to negative Poisson ratio, but most importantly, including a mode of shear. And this allows us to take this structure and switch it between all these different encodings, but there's many more encodings you could do that would be invalid. And what we can do is search this parameter space and build a structure that when you collapse it, you can encode information in. So here we have the entire alphabet in 2D, or we can do 3D structures like this heart that pops out when you compress it. So here's what it looks like. We take many layers. Compress it together. And we program these different outputs. There's the heart. And what we want to use these for is both physical displays, reprogrammable digital fabrication efforts, but if we can miniaturize these, we can start to make shape-specific grippers. We could say, change this pattern every time I'm grasping and making it a reprogrammable, essentially mechanical texture for different gripping surfaces. Cool. We can program these. What else can we do? Well, we're also interested in printing to change the bodies foams are made, or materials are made of, like this foam. So this is work I've been working on literally since I was an undergrad, where we came up with this process called viscous thread instability printing, where you can drizzle honey. It's, same process, but if you do it in 1D, you create a fluid line. These are well-studied fluid mechanics phenomenon by other people. My contribution was I figured out, hey, if you do it on a 3D printer, you can, in 2D, create non-woven textiles, and 3D create foams that you can do with anything from glass to food to silicone. So I've done the food and silicones. Neri Oxman and others did the glass work. But we can build essentially any material you can stick in a 3D printer, we can make a foam structure out of. And what, in collaboration with Keith Brown and my student Brett Emery, we discovered was, and as well as Daniel Revere, we can control these properties. We can dynamically change the height and offset in the materials and transition the material properties. And by throwing a whole bunch of 3D printers and automation at understanding this process, we could design the material properties of foam. And once we understood this input-output mapping by using data-driven methods, we could do things like create discrete gradients in a single print where we change the coiling parameters and stiffnesses, or create linear gradients as we went across. And so now we can create spatially graded foams. We can program in the stiffness and the porosity wherever we want. And this allows us to make things like discrete joints. We can take a box that folds up. Or when we apply it to robots, we can make a robot hand where we can take a structure and we can program in hard and soft regions. When you apply a cable, it pulls, and you can get actuated joints into your structure. So we're interested in using 3D printers to make new types of foam bodies for robots, as well as then making them tendon-driven so we can actuate them. So this is applications in filters, bioscaffolds, food and cushioning, as well as robotics. And we're really excited about our ability to program foams now for robotics applications. I'm going to be conscious of time, and so I'm going to go into this last section, which is how we can use 3D printing to change the way we think about making grippers for robots as well. So if you think about most robotic grippers, especially when you're using it in a manufacturing context, this is what the problem looks like. This is work I did with Adriana Schultz and Ian Good. If you take a bunny and you say, I want to manufacture this and I have to pick it up and put it here. You have a robot and you have a gripper. An engineer might select the gripper and then just say, code, go figure out how to move this robot with this gripper to pick up this object. And all the problem is on code. What if instead we said, well, what if I just pick the shape and I get the gripper and the robot and design them together so it's an easier problem? And not only that, I don't think I need this many degrees of freedom, right? I talk about how great motors are, but they're expensive. Let's do it without motors. Let's use what we call passive grippers. They require no extra actuation, no extra programming. There's no power requirements. They're easier for human-robot interactions. They're less complex, less expensive. Downside is they're less versatile, right? So this forklift can pick up the pallet. It can't pick up the screw gun, and it can't pick up the soda can, unless you're really skilled. And so what we said is, well, who's been looking at passive grippers and how they work? People have been looking at actuatable and conforming grippers, but really the work that I find the most exciting is work by Mark Yim, where they show that you can take different shapes and like loop down onto a structure and grab it without any additional degrees of freedom in the gripper. And so we said, okay, well, we've got 3D printers and we've got design optimization. Can we custom manufacture grippers on demand and make that easier than programming the robot on its own? And so the idea is we take an input object, we have a position of a robot, and what we need to do is generate the gripper and the robot together so that it just locks into place. Now, this is a simulation, but this is real life. You can design a gripper, have 0 extra degrees of freedom, and pick up an object. The way it works is we take our input shape, we generate a whole bunch of grasp candidates, we then try to optimize the different trajectories until we find one that works, and then we run topology optimization to build us a gripper. And so our first step is by understanding the grasp as an abstraction, by defining contact points, and just making sure that the object is stable under those contact points. Then we need to make sure that those contact points can reach back to the robot. So we have to build a skeleton around an object that can combine those contact points back without intersecting with the object we're trying to grab. And that gives us a reduced search space. We can just search over grasp configurations for stability, and then we co-design a skeleton and a trajectory together to check for collision with the object. So if we have something that's not stable, we ignore it. But if we find something that's stable and has a trajectory, we've got a solution. And so what does this type of optimization look like? It kind of looks like this, right? It jiggers around until it finds a shape, and then it defines a bounding box where the robot arm could move and grab the object. And from that bounding box, we feed it into topology optimization, and we get a 3D printed shape. To test this idea, we looked at engineered objects. We looked at the robot, the Stanford bunny, because computer graphics people need that. We looked at a subset of the YCB data set, And we looked at challenge objects specifically designed by DexNet to be hard for DexNet to grab. And what we found is passive grippers could pick them all up. Right? In simulation, we could find shapes, and they had really interesting engineered properties. So some of the grippers had inserts where they would just insert and lock into an object. Others automatically generated tongs to grasp things. And others created a wrench where it used 3 points of contact to wrench around an object. And the trajectories kind of broke down into either front inserts, side inserts, or twists. And we didn't tell it to do any of these, it solved for it automatically. And it's not just in simulation, but we could also find you leverage the bilateral symmetries or the inner structures of an object to make it graspable. And when we printed it and did it in the real world, we were able to grab these objects. So now we have this method of leveraging a body that's already existing and just rapidly using 3D printing to retool a manufacturing process by co-designing the trajectory and the gripper together. And this trajectory gripper co-optimization even works with additional constraints, so we can grab this object right out. It figures out how to go inside and grab it to lift it out when we say you can't touch the surface. So all this work has allowed us to look at how we can build different types of robots. We wanted to make them motor-driven and efficient and able to be useful in manufacturing contexts. We found that handed shearing auxetics allowed us to turn twists into extension, and that gave us a whole new design space to look at, both in traditional robots and soft robots. We found that if we looked at revolute joints, we developed these torque transmitting structures that could make robot arms with new capabilities for manipulating their environment and doing manufacturing tasks. And finally, by leveraging 3D printing, we can make either foam structures or torsionally resistant structures or custom grippers or shape programmable grippers that will expand the capacity of robots to have the right gripper for interacting with their environment. So obviously this work was done with a lot of funding, so I'd love to thank all my funding sources, but more importantly, the students who actually do all the work while I just make PowerPoint slides and beg people for money. So thank you very much, and I'd love to take any questions.
I think so.
Great. I was really interested in the 3D printed grippers. What's the pipeline and how automated is it? So how long does it take for you to give it a shape for it to give you a gripper and a trajectory?
I'm actually going to let one of my students is on the call right now, who is the most recent person to set it up, and he was not on the original paper, so he can be the most critical. So Jacob, can you answer that question?
Yeah, so I recently set up our GC, the grasping candidate software with the topology optimization, and I used it to grab a variety of just simple objects, cylinders, domes, cones, and it was able to run the program on a standard laptop and produce all that the necessary files to produce a gripper in only about less than 10 minutes.
So the longest part of the cycle is really the printing, because usually printing takes overnight.
Yeah, the printing and honestly, just like going over all the features in the software takes longer than it does for the algorithm to give you all the answers.
That's really advantageous, right? Because if you can 3D print something in a few hours and put it on an industrial manipulator, it's a lot quicker than trying to program the control and do trajectory optimization that way. And if you have a repetitive industrial task, then one gripper is enough to just keep doing the same task.
Yep. So you get it. That's exactly the motivation. What this is great for is repetitive industrial tasks. What it's terrible for is working in a warehouse, right? It's like Amazon does not want this, but a manufacturing plant would.
Hey Jeff, great talk. I am particularly intrigued by the notion of transferring torque through a fully, continuum robot structure. I would call it a continuum robot, right?
Sure.
Where do you see the next steps going with the architecture? Like, will you be sort of further exploring, like how far in this current work have you explored the workspace and looked at sort of the various like maximum limits, and also maybe have you thought about other morphologies of coupling this single continuum robot into multiple segments next to each other, or into like stuff like different kind of architectures, how this could be coupled? And what
so
would like a lot of hand
great,
assembly?
great question. I'm trying to pull up a slide. So Kuba, who's on the call, is one of the two students who did the work. Here we go. So he's got a new result coming out as soon as we're done writing it and getting it through review, where we're showing it doing more things you can do with this torque on the end. And so this design was kind of iteration 3 of the structure. And iteration 4 is going to have a lot more power that we can put through it. So what's our expectation for iteration 4, Kuba?
Yeah, so for the next gen, we're actually building an entire new arm for the mass robotics competition. And it turns out with these initial cells that we have, they're fairly stiff, but they weren't actually optimized in terms of their torsional stiffness. And so with these new gen cells, we're targeting a Newton meter of torque through the entire arm. And so a single cell could obviously output a lot more torque. And so as you chain them together, as with any material, it scales as 1 over the length. So that's our current target, is 1 Newton meter through the arm.
Thank you.
Yeah, and then in terms of what you can do, I mean, we can transmit n numbers of torque to your output point. And so then the question becomes, what can roboticists do with n numbers of torque? Everything we do in the rest of robotics. You can put on any type of gripper that uses rotation. And so one of the things we're looking at, we have a paper coming out soon where we put an HSA at the end, and we use it for different operations in continuum robots. So either for bending, anchoring, or extending, and we use that to improve the navigation ability of continuous robots more in a medical context.
All right.
Hey, Jeff, thanks for the talk. I have one question. These shearing auxetics and the way you build them, what is the lifetime of them? Like how often can you rotate and deliver torque before they fall apart?
Yeah, it really is very dependent on the material to make it out of. This is where I'm very grateful that Ryan Tooby has dedicated an entire postdoc to answering these questions. Not his postdoc, but a postdoc in his lab. And so they found that they can build a new TPU one that can last many, many, many cycles and put out more force. So I think you should expect to see that at RoboSoft coming up in your fair country. And when you make them out of PTFE, you can actually, I mean, I had this one here 7, 8 years so far, and it's still going. Now, granted, it hasn't been live in a robot, but it should, last the fatigue life of a PTFE hinge. And then the spring steel ones, they'll last forever as long as you design them right. The really tricky thing is we've been making these on the carbon 3D printer, and that material just has a shelf life like most 3D printed materials that are like SLA driven. And so they just don't last forever. They'll be great for like 6 months, and then the base material degrades, regardless of the fact that it's an HSA. The PTFE ones, they're not going to have that property. You have to design them to not yield in the joints. So it requires really like thinking about your stress concentrations in the design. And the spring steel ones will last a lifetime as long as you don't overdo it.
Thank you. There is one more question in the chat. I'm reading it from Lisa. It's thanks for the great presentation. What kind of materials can you print for the foams, and for softer materials like food? What pore sizes can you reach, minimum and intervals?
Yeah, so good questions. The foam, Brett is also on the call. He could talk about, but most of what you see here is TPU. So this is a TPU orthotic I'm holding up to the camera. Oop, no, it did not like that. You can also do it out of PLA. You can do it out of really anything you can stick through a 3D printer. The challenge is not getting it into a structure. The challenge is getting it to bond well in that structure. So if you take in and use nylon, for instance, as what you're trying to make a foam out of, you're not going to get really good bonding between the layers. But if you use TPU, it'll bond really well. In terms of foam, in terms of food, it really comes down to the extrusion process and how much pressure you can generate. So we've gotten, in my past life, these are like my past sins I'm atoning for. We 3D printed Cheese Whiz. Is that even legal in Europe? Do you know what Cheese Whiz is? Okay, it's cheese in a can. I feel like importing that must be a crime in Switzerland. Like, it's just wrong. But it's very liquid. I think it classifies as a dairy product more than cheese, and you can extrude it out through nozzles down to about 24 gauge. I'm not sure what that is in millimeters, but you can get it through very small orifices. If you want to go smaller, there's actually a way you can do it using electricity called melt electrowrite. And so people can actually, if you apply enough voltage across a goo coming out of an extruder, you can then get a jet to come out, and then you can use the coiling process with that jet. And so scaling it down actually goes quite far. In terms of scaling it up, Brett, whose camera's on now, what's the largest thing you've made, Brett, in terms of nozzle diameter?
In terms of nozzle diameter, this last summer I was interning at Oak Ridge National Lab at their manufacturing demonstration facility, where we had the opportunity to use their extremely large BAM systems, big area additive manufacturing systems, that had a nozzle size of about, I'd say, about a centimeter in diameter. And so the coils that resulted from that were on the order of maybe 5 to 10 centimeters around. And we were able to print very large coils with that. And even on a machine with 0.4 millimeter diameter nozzle, like a standard FDM machine, where I printed coils up to probably about 20 centimeters in diameter. The upper bound, and you end up running into more viscosity limitations rather than actual coil diameter limitations at that point.
Yeah, so we're interested in exploring size scales is the answer, and you should be able to push it up, and there will be some fundamental. Oh yeah, and on the screen you can actually see our lab logo out of the giant coils.
Do we have more questions in the room? We don't have more in the chat, I guess.
This was from Melinda, right? Yeah.
Yeah. Okay, hey, thanks a lot for the great talk and really exciting work. Thank you.
Thank you, Jeff. Thanks a lot.
Fun.
See you.
See you at RoboSoft.